Good morning, everyone. So today, we are very excited to have Yu Chen from UCL to present her recent work on instrumental variables. Yeah, Yu Chen, you can start when you're ready.
Okay, great. Thanks, Chi, for inviting me. I'm very excited to talk here today. Today, I'm going to talk to you about how to perform causal effect inference, in particular, average treatment effect inference, when the treatment undergoes measurement error. So the treatment variable that we measure are themselves corrupted with measurement error, and I would like a method for nonlinear estimation, and in particular nonparametric estimation. And I'm going to use an instrumental variable for it. So that's the goal today. I should thank my wonderful collaborators, Limo, Arthur, Matt, and Ricardo. Just to set the scene for this particular work, I'll go through this quickly because you already know about causal inference. So I'm thinking about scenarios taking place in a school where the teachers of the school wants to know how grade retention, by which I mean repeating grades, would impact the student's cognitive outcome in the future. So they want to know about this structural function f. So the problem is there might be some confounders, for example, cognitive ability, which can influence both whether the student needs to repeat grades and how they will do in the future. So causal inference here is about disentangling, if you like, these two paths, the causal paths and the backdoor and the confounding paths. And in particular, we would like to do this from observational data. So, ideally, I would just like to have data where some students need to repeat grades because somehow they're not doing so well in school due to ability, and some students don't need to repeat grades because they already do better. And then along with their natural outcome, I want to start with those data and ask about what would happen if I intervene on this variable A, i.e. making everybody repeat grades. How would that on average impact their future outcome? So I would like to have the left-hand side from the right-hand side. So recap is in the case where everybody is observed, I can have identifiability from backdoor adjustment. Using some standard conditions like positivity. So what are the obstacles with this? One is even when U is observed, I can still have disentanglement issues. For example, U might lead to imbalanced data sets, which exacerbates this problem called regularization bias. But the problem that we're going to focus on today is actually more the second issue, which is that when we have latent variables in this three-variable graph, that can lead to non-identifiability, which is in some sense a more fundamental issue because you don't even have mathematical identifiability here. So where can latent variables arise? They can, a relatively well-studied case is where the confounder is not observed. And in this case, you have more classical methods like instrumental variable regression methods, where and in more recent times, there's a thread of work using proxy variables, where proxy variables are like imperfect snapshots to the unobserved confounder. Extending from this, there is no reason to assume that only the confounder is unobserved, right? So I suppose the scene that we place this work in is we would like to have a tool which social scientists can use to infer causal effects on their data. And social science data have, they have a reputation of having a low signal to noise ratio. So which means that in their data, a lot of the variables they're interested in are not precisely observed. So this might even include the treatment variable. And sometimes, maybe the outcome is also not observed. But here today, we're going to focus on the second scenario, where the confounder is not observed and the treatment is also not directly observed, or is only observed up to some measurement error, which we will make precise the measurement model of. So why do we need to relax observability assumptions? When only the unobserved confounders are present, we have the very well-known Simpson's paradox, where you so here the left-hand side is a regression line you fit across the two clusters without controlling for the confounder, and you realize that this gives the opposite sign for the correlation compared to the right-hand side where you do control for the confounder. So this example I'm sure you all know very well. What's perhaps less well studied, at least in the machine learning community, is where the treatment is also not observed. So here I want to give an example where in this open study in 2001. These people studied how the long-term saturated fat intake in women would impact their long-term likelihood of contracting breast cancer. So here, their genetics could be an unobserved confounder, and now if we zoom in and think about how they record this long-term saturated fat intake, so they do this by survey. By asking a selected group of women their dietary intake, basically. So when this happens, you can imagine that some people might have some internal bias in what they want to report in the survey. If they have been not behaving and having unhealthy food, then maybe they have some psychological tendency to not be honest about that. And in general, survey data is known to be a source of high measurement error. And what I think make this study really compelling is that later on there is a corresponding study which measured the saturated fat intake from some biological label, and which is seen as a near perfect measurement. And then they compared the measurement from the two different measurement methods, and they can see a very large amount of measurement error, basically. And according to Carroll's book, sometimes you can have measurement error that's so large that it actually accounts for over half of the spread in the regression line that you fit. So just to give you an illustration of what measurement error can do. So this is a comparison of curves fitted by three different methods on data with measurement error. So the pink line is the true structural function. The green line, so the green almost straight line here, is fitted by this method called kernel instrumental variable regression. So this is a nonparametric method, which is provably consistent on data with unobserved confounding, but also with observed treatment. So what you can see is that the measurement error here, which is additive, it smudges out the curve in this fitted line. And this is very intuitive because the measurement error is additive, because you can see that the squiggles in the horizontal direction kind of masks this curve. And to give you a quick teaser, so this red line is the one fitted by our method, which recovers this line very well. Okay. So today we're going to, the method I'm going to outline focuses on the scenario on the right-hand side. So before I dive into my method, I want to recap on this classical algorithm of identification with IVs, because our method is going to base on that. So in the setting with instrumental variables, you have this sort of graphical setup where you have the the usual 3-variable model with an unobserved confounder, and then you have this external Z. That's like this exogenous Z, I mean, that has an arrow into A, but it doesn't completely erase the arrow from U. So identification would be based on the following assumptions, where first you need to have an additive noise assumption where this epsilon comes from U and it's uncorrelated from the instrument. Then in this case, your average treatment effect is simply this the structural function f. And how to recover f? Well, f is the solution to this ill-posed integral equation here. And in the linear case, this is very intuitive. It's just that in this case, y is just some constant coefficient times a plus some noise independent of or uncorrelated with z. And a is also a linear, a constant coefficient times z plus some exogenous noise. And then by rearranging these equations, you can tell that y is that now beta times gamma times z plus some exogenous noise. And so to recover the beta, just need to regress z to y to recover the beta and gamma, and then to regress z to a to recover the gamma, and then divide it out. So here I just want to be mindful about the assumptions of instrumental variable models, which is that I think they need to have strong assumptions. One is that you need to have this additive error model where the additive error is uncorrelated with the IV. And secondly, we need to have this relevance condition where this is basically saying Z is not independent of A in this graph represented by G. And the third one is really what I think a really strong assumption, which is that if we remove the arrows coming into A in this graph, then Z is going to be independent of Y. So this is a very strong assumption, I think, because so for example, in some economics papers, different papers have used the same instrumental variable, for example, rainfall, on different actions. So then immediately we can conclude that only at most one of those papers are correct, right? Because they can't all be correct. Because if they're all correct, then you will have different paths from Z going via different A's to Y, and that would just already violate this third condition.
So can I just ask, so you mean that they've used different the instrument for different treatments for the same outcome?
Yes. Yes, there is actually a reference for that, which I can find later if you want.
Thanks.
Okay. So yeah, so using the same IV for different actions. So yeah, so with this strong assumption in mind, we can yeah. So if somehow these assumptions are observed, are achieved, then how are we going to recover this f? So this integral equation is still an ill-posed one, right? And if we're not in the linear case, in which case we can use linear two-stage least squares. But if we're not in the linear case, then how are we going to recover the f from this ill-posed inverse problem? So the idea of KIV is that, of kernel instrumental variables, is that if we're allowed to say, so first think of the finite basis case. If f is just some finite theta inner-producted with some finite basis, finite vector of basis functions, then this Then this integral equation simplifies to just the right-hand side equals the vector of coefficients in a like transposed times the expectation of the basis vectors. And so we can just first learn these expectation of basis vectors and then regress this to recover the theta. And that gives us that recovers the f if we assume f lies in this space of finite basis function combination. And so this already is the intuition of KIV, I think, except in the kernel's case, you assume infinite basis functions. And to induce well-posedness, we would need to assume that f lies in this RKHS, which is the kind of smoothness condition, and then we impose Tikhonov regularization to I guess make the solution unique. Okay, so
what is Tikhonov regularization?
My understanding is just that it's just this regularization where you penalize by the size of f in the RKHS.
Okay, thanks.
Yeah. So then what happens if A is actually unobserved? So this is what we propose. So in the case where A is unobserved, I need to require two observed measurements of it. And these two observed measurements needs to satisfy the following conditions. We need to assume additive noise on the measurements. So M is just the treatment plus some noise. N is also the treatment plus some noise. Both of the noises, well, the first one needs to be uncorrelated with everything else. And the second one does need to be independent from the action. I get that there is this asymmetry here, which feels kind of unsatisfying. But there isn't more I can say about this apart from that this is a technical condition which is needed in the proof of in the proof for identification for the for the latent variable distribution.
And can I just ask, so do you have any counterexamples where you just assume uncorrelatedness? It doesn't work, or is it still open?
So I haven't thought of a counterexample, to be honest, but in the proof, at some point, it needs to basically use the fact that they're independent to do some factorization. So if they're not independent, then you can't do this factorization of the, yeah. And in my understanding, sorry, yeah, go on.
So you say there's some sort of asymmetry here?
Yes, so like asymmetry being like, how come this the delta n needs to be independent, but delta m just needs to be uncorrelated?
And so in practice, you can never know this. Huh?
Yes, that's true. In practice, you can't. You can't verify that. Like that they're independent or uncorrelated. But there are stuff you can do. For example, if you have more than two measurements, then
but
you
would have those two, and you decide to use one as m and the other one as n. In practice.
Okay. In practice, like, how do you know if you've oriented them correctly, right?
Yeah.
Yes, I think this is indeed hard to testify. But one thing you can do is, if you have more than two measurements, then you would have over-identification. Yeah. So then that can allow you to test, whether you've oriented them correctly, because you just take different pairs and compare. Right?
Okay. And so if you go back to the linear model.
Yeah.
So if it's just an additive measurement error, and in the linear model, I can say, well, the instrument Z is not as so if the measurement error is independent of Z, then I don't have a problem, do I?
If the measurement error is independent, yes. So in the linear case, you actually generally don't need two measurements. You only need one measurement.
Yeah. Okay.
And I think
that would be an interesting benchmark to.
Yes. Yeah. Okay, fair enough.
To compare things to. Because some of the models you look at are linear models.
Yeah, that's true. That's true, actually. Yes. But
so that's what I would always say. So my instrument is independent of everything else. Then I'm done.
Yeah, if the in in the linear model case, yes, you can use kind of use the instrument as a second measurement. That's true.
No, the instrument is an instrument for both A and the mismeasured A.
Yes.
And if it's independent of the measurement error, then of course you get a consistent estimator in the fully linear setup.
Yeah, that's true.
So I'm slightly confused. Do you actually need A to be continuous?
Do I need A to be continuous?
Yeah.
Yes, because of the instrumental variable assumption. This needs to have an additive error.
But A itself is the treatment.
Oh, yes. A also needs to be continuous because if A is categorical, then you can't have additive error on.
Yeah. So why do you have examples where you have A to be binary in the paper?
Sorry, I can't hear you. So why do I have?
When you talk about grade retention, that's a binary indicator, isn't it?
Oh yeah. Okay. Fair enough. Yeah, so I use that example as a motivation example, but yeah, it's true. The A.
Yeah, but then it doesn't apply. So I think it's a bit dangerous to use examples where your method don't apply.
Okay. Yeah. Fair enough.
Okay. Thanks.
Yeah. Okay. Yeah. So assuming additive noise on the measurements, where the additive noises have this independence and uncorrelatedness conditions. We also, alongside this, we also need the usual instrumental variable identification assumptions. So again, additive noise on a nonlinear response, and the IV structural assumptions of relevance and this Z independent of Y in the graph where incoming arrows into A are erased. Then yes, so here I want to briefly talk about the application scenario of this. Because one thing that I think might not be clear is how useful is like how strong are these assumptions? When are they actually satisfied? And this is where I think feedback would be useful because I get that there are experts on IVs here. So one issue I encountered during this project is that when I was trying to find real-world examples, in many examples I find the instruments are very weak. So even if they call it, they're somehow confident that the instrument satisfy these uncorrelated with the confounder and all the influences from Z to Y goes via this A. There is still this problem where this Z is basically just very, very weakly correlated with the A. And one example I can think of now is in the study by Hanushek on investigating civil conflict on the investigating the impact of GDP on the civil conflict of a country, they used rainfall as an instrument. So they argued in the paper that this satisfies these instrumental variable conditions, but they also admitted that the relevance of this instrument is very weak, and this was testified in my experiments. So basically, when you try to fit a line from rainfall to GDP, you just get something that's almost just flat. So I think it's important for me to say that when you want to deploy this, when you want to use this method on some real world problem you have, I think you had better have the resource to perform some kind of experiment. So for example, if you're in a school and you want to understand how skills, let's say scientific reasoning skills of students is going to impact their long-term like career outcome, then you can measure their then you can measure their scientific reasoning skills by some test scores, which education practitioners will be able to say if they actually fit this measurement model or not. But more importantly, what IV should you use? I think that for the school to be able to use this, they had better have resource to deploy some kind of policy trial, some like imperfectly controlled policy trial, where they try to make the students, for example, they try to introduce more science project components in the curriculum. But this is an IV and not just a randomized control trial, because they don't force students to take more science projects. So if students are ill, then they can stay at home. Or like however much they get out of the science projects will also depend on this confounder. So then in this scenario, I think we would be able to ensure relevance. And also because hopefully the practitioners will use their domain knowledge to conclude that this IV is a suitable IV for the treatment. So it wouldn't have this problem of I don't know the proper terms, but like it wouldn't have this problem of multiple paths from the IV to the outcome. Yeah.
Hi, Chen. Can I quickly ask a question? So probably I don't have a answer to what you asked, but I want to know, you mentioned the issue about a weak instrumental variable being the correlation between the instrument and the treatment being very weak. But in your setup, the treatment itself is is hidden, it's latent. So how do you actually measure the correlation? Or do you measure the correlation between the instrument and the measurement instead?
So the question is how do I ensure it's a strong instrument, right? Because when I can't measure the correlation between the instrument and the treatment.
That's right.
Okay. So because you're right, because the treatment is unobserved, so this is not directly testable. And I think that to measure the correlation between the instrument and the two measurements are doable. Yeah, if the measurement error are large, then that can mask that relationship. But I also think that we can take advantage of expert knowledge. So if educators, for example, already know that science projects have a strong impact of students' cognitive abilities, then I think we can take that as our prior knowledge.
I mean, presumably you also need the instrument to be strongly associated with the measurements, right? Otherwise, either the measurements aren't good measurements or the instrument is a weak instrument. So, presumably.
Yeah, indeed, yes. So you meant like if we measure the correlation between the instrument and the measurement, and then observe that there is weak correlation, right? Then there are two possibilities.
Yeah, and neither of them are very good.
Yeah. Okay. 3 possibilities. Yeah. Either one of them is bad, or neither of them is good. Yeah, that's true. Yeah. But
Thank you.
might. Yeah. Do you have a follow-up question?
Oh, sorry, I just said thank you.
Okay. Okay, cool. Yeah, so if you have feedback about like this instrumental variable suitability point, then I would love to hear what you think. Otherwise, let's move on for now. So the overview is that the overview of our method is that given these assumptions on the noise, there is this old result called Kolotsky's lemma, which recovers the characteristic function of the latent variable from functions of the characteristic functions of the measurements. So here the left-hand side is the characteristic function of A, and this quantity here is the characteristic function of N. And this quantity here is also a function of the characteristic function of M and N. So in particular, it's the quantity you get when you take the characteristic function of M and N and differentiate it with respect to the frequency of M, and then set that frequency to 0. So basically, on the right-hand side is just a function of some characteristic functions of observed variables. And then you combine them in this way, and then you get back, the car function of it. So now, because I know the Z is exogenous, so I get it for free when I just add condition on Z in this equation. Okay, so now
So can I just ask, is this assuming the additive noise model on the left?
Assuming these conditions, yes.
Yeah.
Yes. Yeah, right. So now, if we're willing to make some parametric assumptions on the response function f, then we're kind of done. Because we can use this characteristic function of a given z to get expectations of the basis functions by convolving the Fourier by convolving the Fourier transform of basis functions and the characteristic function. And then once we get the expectation of basis functions, we can just regress the expectations of basis functions to the expectation. To the conditional expectations of the y's, right? As we said before, when we assume the response function lie in the space spanned by finitely many basis functions. So this kind of already works if we're willing to make a parametric assumption. So now the question is, can we do better and have non-parametric estimation? And the answer is yes. And also here, I should point out that although I am making additive noise assumption, I'm making no distributional assumptions for the delta M and delta N. And this is a flexibility point for our method. So now how can we have non-parametric estimation? So now the idea is to build a bridge from the characteristic functions to the conditional mean embeddings, which is this quantity that's just the expectation of RKHS features taken over the measure of a given z. So the kernel ridge regression estimator of this CME mu hat n of a given z is nothing but a linear combination of the kernels centered at the AJs, where the AJs are the for now for now, ignore the fact that the AJs are unobserved. So basically, the CME is a finite linear combination of the kernels centered at the AJs, where the and now we can construct this estimator of phi hat n. So this estimator of the characteristic function of a given z, by also taking the same linear combination, but now it's the linear combination of the Fourier bases, where the gamma hat and j's are the so these are the coefficients in this linear combination, and they're given by this kernel ridge regression estimator, where this lambda is the regularization parameter in KRR. So now we have this result in the paper that if we have a translation invariant and characteristic kernel, then the two estimators of mu and phi, they both converge to the true quantities with the same rate under the measure given by the inverse Fourier transform of the kernel. So, given this insight, we can say that now we assume f lies in this RKHS of A. So then the expectation of y given z, which is just the expectation of f given z, and if we put f into in its RKHS, then this amounts to taking the inner product between f and the conditional mean embedding, which is like the conditional expectation of these infinitely many basis functions, right? So yeah. So then we just need to get the CME of a given z. And how do we get them? We can approximate them via the phi hat n of a given z, which we can obtain from equation 1. And this is because they both just depend on this gamma hats and the AJs. So as long as I can approximate this thing under this form, I can just grab the gammas and AJs out and plug it right into this formula, to this estimator of the mu hat n's, and then I get an estimator of the mu hat n's. And once I get that, I can regress from this quantity, the estimator of this quantity, to the y given z to recover my f. So now the question is, how do I get the estimator of the phi's, right? How do I get phi hat n's? So I can get it from equation 1, but I also need to get it in this form. So now I will talk about how do we get it in this form. Yeah. So notice that in equation 1, basically all of the quantities on the right hand side, they're just functions of some characteristic functions. And then I can use that bridge the other way around. So I can approximate these characteristic functions with the CMEs of the corresponding quantities. So I can learn the CME of n given z. I take the gammas and the nj's out and plug it in here to get an estimator for this. And similarly, I do this I need to take a derivative. But yes. Now another thing is, after I obtain estimators of these quantities, I still need to perform this integral, which is fine. But here we propose to speed up the process by removing this integral. So we take the log on both sides and then differentiate with respect to alpha to remove this integral, and then we replace the differentiated quantity with the sample estimates, which the sample estimators, which we described in the previous slide. And now a point that we need to make is that because differentiation is a many-to-one operation, So how do we know that after we've differentiated equation 1, the solution we get from the differentiated equation is the same as the original solution? And we can check that this is fine, that this differentiation doesn't introduce more solutions, because basically the space of characteristic functions is normalized. It's always 1 at 0, so it can't introduce more solutions. So this is the equation we get after taking the log and differentiating and replacing with sample estimates. And now we can obtain the gammas and the AJs associated with this quantity by basically minimizing the discrepancy of both sides. So this leads me to the MEKIV algorithm, where in the first stage, I use kernel ridge regression to learn the conditional mean embeddings of my n given z and mn given z. And then by this bridge to the characteristic functions, I take the gammas and the samples from there and plug it into the estimator of the characteristic functions of n given z and mn given z. And once I get that, I do step 2, minimizing the discrepancy of two sides of that equation to get an estimator of the phi n of a given, the phi hat of a given z. And once I've gotten that, I again grab the gammas and the AJs out of there and plug it into the estimator of my mu hat n's. And once I have I have my mu hat n of a given z, I perform kernel ridge regression again and get my f. So the advantages of this algorithm.
A very quick question.
Yes. Yeah, sure. Should I go back?
Go back to the previous slide. So the n is a sample size and s is a sample size. Is that right?
Sorry.
So you have n. So you got j is 1 to n on the left. Step 1.
This step 1.
Yeah. What is n?
What is n?
Yeah.
So,
No, not nj, but yeah, you got 2 n's.
Oh yeah. Sorry. Yes. This should be. I think. Yeah. In the paper, I replaced this by s. Sorry about that. Yeah.
So that's a sample size. Yeah?
Yeah, that's a sample size. Sorry about that.
And then in step 3, you have a different sample. Is that right?
Yes. So you need to have. So this is something that's discussed in the kernel IV regression paper, where like you basically need to, well, yeah, for 2SLS you need to split the sample into 2 samples. So you do first stage regression with the first sample, second stage regression with the second sample.
So you do split sampling?
Yes. Okay.
And that's to problem of overfitting, is that right? Otherwise?
Yeah, because you don't want problems with autocorrelation.
Yeah.
Yeah.
Okay, so but then if you split your sample, do you then do it both ways? So do you repeat sample splitting and then average or not?
Right. Yeah, this is something you can do. I think they do that in some papers to improve accuracy, but in this work, I didn't do that because I'm just focusing on the new method that we proposed.
Okay, but if you have a weak instrument, then you split your sample, it gets weaker.
Okay. Yeah, I see. So you're saying if I have. So you're saying I can exploit the instrument better by doing repeat fitting?
Probably, because now you just say, so how do you split? Is it 50-50 or?
Yeah, so the split ratio is a hyperparameter that you can choose for simplicity.
Yeah, of course, but what do you do in practice?
50-50.
Yeah, okay. Yeah. So if your F is the 10 to start with, it's sort of half it the first stage.
Yeah.
Okay.
Yeah. Okay, thanks for the comment. Okay, so so just to summarize the take-home messages of the advantages of this method. First is that we don't need to make any distributional assumptions on the measurement error, although we do need to assume that it's additive. And we're only modeling the conditional mean embedding and not the full distribution, which allowed us to use kernel ridge regression, which is which is just an easier problem than modeling the full distribution. And thirdly, different from many machine learning algorithms, which involve a lot of tuning of large number of hyperparameters, we pretty much don't need to tune any hyperparameters. I think there are two hyperparameters. One is the kernel ridge regression regularization parameter. And the other one is something else that I can't remember now. But the point is there are only two hyperparameters to tune. So we run this on synthetic data. So unfortunately, didn't manage to run it on real-world data because the data I found have this weak instrument problem. So you can see that we illustrate from synthetic data, where like these simulations have also been used in previous works, like the KIV regression. So we extend their experimental framework by adding noise on the treatment that they assume to be observed, basically. And you can see that as the measurement error gets large, our method shows its advantage more and more. So the pink one is the KIV oracle. So this is KIV where the treatments are seen. So this is something that we can't hope to beat. And the other two are so KIV with KIV that takes the corrupted treatment as the true treatment, or it takes both corrupted treatments and take the average, hoping to remove some hoping to like decrease some variance. So comparing these four things,
sorry, can I ask a very quick question?
Yeah.
So in the top ones, you don't have confounding, is that right?
In this one.
In the top four, is that the?
Oh, in top four.
Got confounding
we
in
always
the,
have confounder.
Pardon?
We always have confounders. Yes, it's just that in this demand design, the confounding can also be tuned. So we tuned different levels of confounding. But in every experiment, we always have unobserved confounding.
Okay, but you. Thanks.
Yeah. Okay, and I list Gaussian and mixture of Gaussians to illustrate that our method is free of distributional assumptions. So it continues to do well when the measurement error distribution is multi-bumped. Okay. Yeah. So the future directions of this project are. First, I would like to relax this additive error assumption because I think that in a lot of social science applications that I have seen, for example, survey data, a different kind of measurement error assumption is used. And this thing is called Bergson's error, where the measurement error is not assumed to be independent or uncorrelated with the true treatment, but the other way around. So instead they assume that the true treatment is the measurement plus some error. So then the error is independent of the measurement. And also currently this work is in the static setting. So I think to be deployed in sequential settings, which is also quite prevalent in like policy studies in education or healthcare, it would be useful to extend it to cases where we can deal with sequences. So yeah, so that's all from me. Thank you very much for listening. Yeah, and please let me know if you have any questions or any useful feedbacks.